Okay, so my interest in functions of many variables comes from involvement in quantum chemistry. For the last 20 plus years, I've been working with other people on problems in that field. And at some point, we decided to try to solve Schrödinger's equation. And that started the process. And when we did our first few experiments, we noticed interesting things which I'll mention during the talk. And as a kind of a comment, I would say that in terms of human intelligence, difference of it from animal intelligence is that we can handle functions of many variables. So language, things like walking. You can look at, the algorithm for a fly, how it flies, how it controls flight, is extremely simple. There was a beautiful talk by, I forgot the name of the person from Cornell. It's about as complicated as PID controller, cruise control in your car. It's very, very simple. And then you go along the sort of evolution of animals, things become more complicated. But then you notice that, for example, a gazelle, when it's born, it can run almost immediately. As you go further, well, let's jump to people. Human babies take a year, about a year. If somebody has injury to the spine and they learn to walk again, it takes about a year. So the algorithm of learning has this feature. It's very slow to learn, but then once you start walking, you can do it very quickly. And if you look at how engineers handle control, they try to do model reduction. So you have many, many states, and they can try to build a model that has fewer states. And they're very successful on that. But when you look, say, at videos of Boston Dynamics, I can tell you that's how they build it, because the movements are not natural. So, and kids learn to walk, say 1 year old, they start walking, and 1.5, they are running. And now a kitten takes maybe 2 weeks or 3 weeks. So you can sort of see that this particular function requires functions of many variables, especially in humans. Now, my interest, as I said, comes from more or less physics. And here are some observations that follow from what we did. So first one is that you have to dispose of standard definition of a function. Now, what do I mean by this? If you look at analysis, people have functional spaces in 2, 3, even 4, maybe 5 dimensions. It's fine, it works. But then you need to deal with curse of dimensionality, and there were many attempts to make functions basically lower the dimensionality by introducing, small derivatives in different directions, things of that sort. None of this worked. If you basically such constructions always had constants to power of dimension. So if you want to deal with curse of dimensionality, you need to do something else. And the idea is to use some structure. So describe a function by a structure. Now, with a structure come algorithms, because without algorithms, you can invent a structure, but without tools to manipulate it, it's quite useless. So when you go to functions in high dimensions, you may have to change a lot of things. So notion of error may have to be different. So for example, small is usually the kind of standard way of thinking about errors. But smooth error is also interesting because, for example, if you look at a picture which has some discontinuities, you add nice smooth function to it, you can see the same thing. So your vision is not affected by it. So now, representation may not be possible at all, may not be unique. All these things are kind of run against the common view of mathematicians. They're happy when things are unique, exist. But in this world, you may have to give up some of this. It doesn't mean that you cannot use it. Usefulness, and I will give you examples. All right, so I will talk about two structures of that kind. One is what we call separated representation, and I'll connect it to something that other people done well before us. And the second one are the multivariate mixtures. So look at standard separation of variables. You have simply product of functions. Each individual function can be of 1, 2, or 3 variables. And the difference is now that I will have a sum of such things, sum of products. Now, it's reasonable to organize these coefficients in some order, similar to what you do in SVD. And I'll talk a little bit about SVD. And the functions should be normalized to have norm 1, to norm, for example. And then you look to approximate a function by a sum of products. Now, I'm already cheating. Can you see where I cheated? Well, I just told you that I cannot have a function of, say, 100 variables. I can write a list, but I cannot put it in a computer. And in the estimate, I'm subtracting it. So I'll explain what will happen, so this will not be a problem, okay? But you have to think about a function with 100 variables, and suppose you discretize it with 2 points in each direction. You will have 2 to the 100 points, and you will never put it in the computer. So you really have to think differently about it. Now, you can do the same with operators. And that's actually is very interesting and has been very productive in quantum chemistry. So basically, you say that, well, you want to have an operator written as a sum of products, and in each direction, you have kernels which are, say, 3-dimensional, maybe 2-dimensional, maybe 1-dimensional. And here is an example. You take this operator, sum of Laplacians, and for simplicity, I added something to it so that it's a bit positive definite. And you can compute exact kernel for this operator. And I don't know whether you sort of have a picture in your head of Bessel K functions, but ignore that, just look at denominator. It's extremely singular function, very unpleasant. Yet, you can approximate this function with a sum of products where number of terms is logarithmic in the accuracy you want. Now, I don't remember numbers for this particular operator, but for inverse Laplacian, which is singular, so norm will be a relative norm, it will be different norm. For inverse Laplacian, if you want to go from 10 to minus 15 in distance to 10 to the 15, which is 10 to the 30, the size of the universe, you need only 1,000 terms with accuracy 10 digits. So these are very, very efficient representations, and they play a very fundamental role in computational quantum chemistry these days. There are other kernels which can be treated the same way, and there are singular, hypersingular operators, and on and on and on. Now, if you look at this function in the momentum space, it's very simple, right? It's multiplication by this 1 over, and maximum value it reaches is when all p's are equal to 0. So it's a bounded operator, and that's why it sits there in the estimate, okay? All right. So now so I gave you sort of the idea how I'm looking at it. But now let's go a little bit to the history. The history started around 1970. There was Parafak and Canonical. I cannot pronounce those things. So Harshman, Carol, Chang. So I call it canonical tensor decomposition. Okay. It was used extensively in data analysis of mostly three-way arrays. The reason for three-way arrays is because they would collect data, and tensor with 3 indices you can put in the computer. Probably you can put 4 indices, 5, but then you run out of it. So if you want to read more about it, there is a review paper, and we learned about it after what we did, so it was kind of reinvention. But so I want to explain something that is important. What is the difference of three-way arrays versus two-way arrays, matrices? So for matrices, you have SVD. Now, do I need to, can you, the equations for SVD with T, do I need to explain why it's SVD equations? Okay, let me explain this. So if you want to find SVD of a matrix A, you can, for real matrices, for example, you can do it for complex ones as well. You can create this kind of a matrix. It's symmetric. UV, mu, UV. You expand this, you write what it means, and you will get standard ATA, the standard definition which is given in textbook. This is better because you don't multiply matrices. Algorithms for SVD don't multiply. So that's exactly what is written here. So you contract by one index, you get something with another index, and you do the same here. Now, it will become clear why I'm mentioning it. SVD, if you singular values have multiplicity, it's not unique. So here is identity written with, now if you run MATLAB, it will give you the one that you would anticipate, but you can write with different, large number of possibilities. Okay. So you can do something clever, and I tried to do this when I just started on this. Clever in quotes. You can write it, you can write it with 3 indices. So you want to get this. So why not repeat what you do with singular value decomposition? So I contract L2, L3, I get L1, and so on. And the iteration that this equation, if I do iteration, it will converge. So once it converges, I can subtract it from the previous one, from the original. I have the difference, and I can apply it again, and it will converge again. So what's the mode of failure? Well, what pretend to be singular values will decay, but at some point they will stop decaying. They will start to oscillate. So this algorithm doesn't work. Okay? Okay. So there is no analog of SVD in dimension greater than 3. However, there is something else which is not available for matrices. And this is so-called, well, basically there is a condition, in this case for three-way array, due to Kruskal, so-called Kruskal rank. So if you have that representation and you have inequality, which is very mild, then this representation is unique. Okay? In 2D, that's in matrices, it's not the case. Proven by Kruskal, and for general case by Sideropoulos and Bro, 2000. Now, separated representations are a bit more general than canonical tensor decomposition. You will see when I will use them, there are things which you can do with them, but you cannot do with. But if you discretize separated representation, you will always get canonical tensor decomposition. I already called them. So in the previous talks, these were called topics, for example, things like that. We call them directions. Okay. Okay. Now I want to explain. I mentioned these things about SVD and about three-way arrays in order to mention this paper. I learned about this result in 2012 during SIAM meeting. So the problem is the following. You have several orchestras playing different uncorrelated quote-unquote melodies. And you have some microphones. You record this, and now your problem is to separate these melodies. So what they do in this paper, they work with three-way arrays. They use uniqueness, and they did a really good job. Okay. Now, I will have a detour in the next slide. I want to explain. So during one of the talks, I asked whether you need to use model of the eye, correct model of the eye for images, and the answer was no, and I disagree with that. And I'll explain why. So our hearing is actually much more sensitive than our vision. And probably the reason is that at night you can hear lying, some far away where you cannot see. So it's a survival thing. And when you have sound, you have to sample it. If you do signal processing, and sampling is important. So here is, wrong button. Okay, so I inserted this slide. It was not a slide. I wasn't planning to do it. So on the left, there is some insect. Sorry, I didn't even look what it was. Probably dragonfly. Maybe somebody can tell me what that is. And you see the arrangements of sensors on the surface of this semisphere, right? Does anybody know why is this arrangement the way it is? Anybody can tell me. So the answer is no. You never thought about it. Well, what do you see on the right? Do you know what you see on the right? So these are icosahedral. These are quadratures for the sphere with icosahedral symmetry. Discrete group, okay? And you observe similar things. You know, you can kind of see 3 directions at each point, right? Crossing like this. Now, with quadratures, I have to be very careful because not everybody thinks of quadratures the same way I do. So these are optimal quadratures, minimal number of nodes. And when you have properly derived, and it's important, properly derived quadratures, they can also be used for interpolation. So this arrangement of the insect allows it to do interpolation. So these quadratures allow 16 digits. Of course, for vision, you don't need 16 digits. And if you relax it, you have many you have a variety of possible solutions. You don't have unique ones. But these solutions all have this kind of features, directions. And the reason I mention this is that if you want to represent information on this grid, you should use 3 or maybe 4-way arrays. So angular directions, two variables. And then what you want to do is you want to capture a whole neighborhood around a particular point. And that gives you 1 more dimension and perhaps color. Color is not so important, but it may be important, who knows. For insects, I think it is important. So this was now, human eye also has, if you look at how sensors are arranged, they also have curves. So I can talk more about this maybe separately, but it's very, very important to model the things correctly because your image processing will depend on it. And in fact, our eye cannot see critically sampled images at all. So sometimes, somebody defined an image as a critically sampled 2-way periodic array. That's a very bad definition. We can talk about it separately. So I'm coming back to the talk. So you can do operations on separated representations. You can add them. It's simply a merge. You can multiply them. Rank will grow. Separation rank will grow. You can compute in the products. And in all of these cases, the resulting rank will be larger than the components that go in. And so you need algorithms to reduce the rank. Okay? So alternating least squares. So this was used in chemometrics since 70s. I'll describe this algorithm, the basic idea. So you have a separated representation already. Or in low dimensions, you can have a tensor. And it has, I will talk about the way I think about it. So you have some lone representation with R initial terms. And you want to seek representation with fewer terms. So R initial, say, 10,000, and you want to construct something that is 10. So what do? You fix all directions except 1. And if you do this, the problem reduces to L2 minimization, least squares. You solve this problem, you update representation, and you switch direction. And you do it again, 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 and then again, again. Until what? Until you're either happy or not happy, and then you can increase number of terms. Now, to avoid ill conditioning, you need to add something, but you still can have ill-conditioned representations. There is an example of that. And from this point of view, this algorithm appears very unsatisfactory for numerical purposes. Nevertheless, it works very well. Oops, wrong button again. Okay. So when we started, this algorithm helped to discover two analytic results. So I cannot block the right-hand side, but I was working with Martin Mollenkamp, and he walked into my office and said, well, we probably shouldn't do this stuff, because here is an example where it won't work. You see, you have standard formulas for sign. Now, if you use complex numbers, of course, there's separation rank 2. But if you use real numbers and you use standard trigonometric identities, each time you will double number of terms. So it will have 2 to the d terms. Well, we put it into the algorithm, and it came with exactly d terms with machine accuracy. We put a different initial point. It gave different answer with d terms. So 2 days later, there was this new trigonometric identity which was not on the books. You can see that you cannot make sign k, xk, because if you make this 0, you divide by 0. So you have to have the shifts in order for this identity to hold, but algorithm found it. And then another experiment was, so instead of V, it was Laplacian. So we put, now, Laplacian has separation rank D, but nevertheless, we decided to put it in. And it comes out like 7. So we put D 15, it gives you 7. You put 100, it gives you 7. But now it's not full precision, it's approximation. And here is how it works. Consider this function of one parameter, which is a product of this kind. And you notice that derivative at t equals 0 is exactly this. Right? You differentiate, you see it. So you can use finite difference approximation to this function at 0. And this will give you about, accuracy 10 to minus 6. And that's what we observed. Okay? So this was not obvious initially. So algorithm was interesting. And we have 2 papers on this. The first paper is in PNAS. We were given only 6 pages, so it's very terse. And then, with a lot of examples, we have paper in Science Journal of Scientific Computing. It's 2005. Okay. All right. We observed some phenomena very early when we started working just with random numbers. And that you do this alternating least square iteration, and maybe 10,000 iteration, nothing changes. But, we were working with small number of directions, and so it comes, and suddenly you see, boom, a drop. So from the numerical point of view, it's very unpleasant. And because it's pessimistic, we call it swamps. But if from AI point of view, it's interesting, because this is how learning happens. If you try to learn to walk, for example, you fail, and then suddenly you start doing it, and then you do it very nicely. So it's again. So it's called grokking, and I learned this term recently. It has positive connotation. Now, this behavior was noticed in a number of nonlinear algorithms, not only this ones. And Martin was investigating this issue. He wrote a paper not so long ago where he looked at a very simple case, and his conclusion is due to a saddle type situation where Hessian is ill-conditioned, and basically imagine you have a saddle which is very, very long, and you walk along it and walk along it until you fall. So now, and there are also, the problem is that this behavior can also be because you don't have enough terms. So it's not a very easy thing to tell apart. Okay. So at some point, this is the, I have only a couple of slides connecting it to machine learning. So here is a problem. You have a bunch of points in high dimension, and you want to find a function that approximates these points. So regression, multivariable regression. And so what we do, we seek this solution in the separated form. These functions, you can select them from some subspace, but you should not make them, for example, orthogonal. It would be a mistake. So let me explain why. If you put a constraint on how these functions should relate to each other, then a sum like this, where there is no constraint, will require 2 to the d terms if you put constraint. So basically, orthogonality between functions is not your friend in high dimensions. And in quantum chemistry, people were doing Slater determinants, and they were initially using orthogonal things because things come kind of orthogonal, but not really. And then they relaxed it as well, they noticed it. So, so basically, you should avoid putting constraints as much as you can. So for regression, ALS collapses basically the problem to a sequence of one-dimensional optimization problems. For example, VLE squares. But you can do other things. Your functions can be polynomials, can be rational functions, can be Gaussians, can be whatever you select, can be wavelets. So it can be multi-resolution. And optimization in one direction can be done by a variety of algorithms. So nonlinear fitting of the, for example, rational approximations, things which are not available. Rational functions don't have nice generalization to high-dimensional spaces, but in 1D, they can do wonderful stuff. They capture singularities. So there is a paper, and there are some examples there. Okay, one more algorithm with separated representations. So pretend that you can read below. So how do you find the largest entry of a vector? So I give you 100 numbers. How would you find the largest entry? Well, you will write a loop. You go compare, right? Well, it won't work with tensors because you cannot go through all the entries, right? So what are other ways? Well, take this vector, put it as a diagonal of a matrix, square this matrix, normalize, square this matrix, normalize, and numbers which are smaller than the largest one will decay, and you will end up with the largest number, and you can then see its position. So this is an algorithm for separated representation of tensors. So scaling and squaring plus reduction. We call reduction this reducing number of terms in separated representation. This algorithm converges quadratically. So, okay. So this was very good, but not well, I should have said it before. What is the class of functions that admit reasonable separated representation? So initially we were over-enthusiastic. We thought that there is a very large class. Well, it's not that large. I can easily construct function for which you will not have a reasonable representation. For example, if you take functional determinant, it will have n factorial terms, and I can select function in such a way that you won't be able to reduce it. Now, and these functional determinants play a significant role in quantum chemistry, and they work with them. So how it happens? Well, they use a weak form of it. So you can compute in the product between such objects in order n cube rather than factorial. So it's called Lodwin rules. So it's a nice observation, which is widely used. So, but in principle, it's limiting in somewhat. So, oops, again, the wrong button. One more thing. So, algorithm alternating least squares is very expensive. And so we always used it with some kind of preliminary reduction of terms. And the way you do it, you think of all these terms as vectors and simply find linear dependencies between them. So you have many directions, but you still think it's one vector, it's just a collection of numbers. Now, for matrices, this is known as interpolative decomposition, or finding skeleton of a matrix. So think of columns of the matrix. They can be linearly dependent to some accuracy. Find the best subset of them, can represent all other columns. That's skeleton. And so we did skeleton for separated representations by mapping this problem on some matrices. Okay, so there is a paper on that. But that started us in one more direction. And this is considering multivariate functions, multivariate mixtures. And the idea is the following. You have a linear combination of multivariate atoms. And the only condition I put on them is that I can compute in the product between them inexpensively. Now, in linear algebra, when you work with matrices and you compute the skeletons, those algorithms are proportional to n squared, where n the size of the matrix, because you have to apply this matrix to a vector. So it's already n squared. And this is because in the product cost you order n. And here we want this in the product to, it may depend on dimension, but we want it to be independent of other at number of points and things like that. So important example is a Gaussian mixture, multivariate Gaussian mixture. So these atoms are just multivariate Gaussian distributions with some mean and covariance matrix. And the moment this covariance matrix is not diagonal, it's no longer separated. It's no longer separated representation. Okay? So it can be shown that multivariate Gaussian mixtures can achieve any target accuracy when they approximate functions, because now they can adjust to various things. There is actually multi-resolution Gaussian basis as well. Okay, so the algorithm, so again, you need reduction algorithm. So you have, for example, in quantum chemistry, you have an integral. Everything can be represented as a Gaussian. Green's functions, potentials, wave functions. So say you have 100 of each. You multiply them, it's inexpensive. You get again Gaussians, but you have a million of them. And you need to reduce it. You know that many of them are linearly dependent. So the algorithm we have is linear in the number of original functions and quadratic in the number of functions that you get out of it. Okay. The algorithm uses pivoted or partial Cholesky factorization, and we've shown that you get exactly what you would get if you were to have the full gram matrix. So let me explain why it works. If you have positive definite symmetric matrix, which is gram matrix, you can pivot along the diagonal. And so you don't create the full matrix, you create the diagonal, you pivot and create only things that you need for the next step. So it's very simple, and mathematics is there to show that what you get is actually controlled by the smallest pivot that you reach. Okay. Alternatively, you can use rank revealing Gram-Schmidt. We have yet another algorithm in that paper, and it works. And so now let me show you what we have some examples. We didn't do data science in that paper. It was done for the purpose of numerical computations. But we had a couple of examples, and I will show you these examples. So kernel density estimation, very old idea. You have a bunch of points, and you want to construct a function that kind of approximates these points. So you associate with each point a kernel, you write the expression, and the next question, what do you do with this? If you have a lot of points, indeed you can evaluate this kernel, but it's expensive, number n is large. You don't want to use this original representation that you constructed. You want to do something with it. So the standard approach is to go to the Fourier domain, put a filter, come back, usually to equally spaced grid, and you have it. It works. And now selection of this H is a delicate issue. I'm not going to talk about it here, but we used, okay, so as I already said, standard approach, you do Fourier transform. And the problem is you cannot generalize it to high dimensions because although it's a fast algorithm in 100 dimensions, it's no good. So our approach doesn't require FFT. All we do is we select a subset by this algorithm that I just described. And it's linear in the original number. So we did this example, not very large number of points, but coming with no noise. There is a way actually to remove noise doing this kind of stuff, but it's not written in that paper. And you can see that we were doing numerics. We copied this parameter h from Mathematica with so many digits. A data scientist wouldn't do that. So Mathematica reduced it to 241 points centered at the equally spaced grid. Our reduction gave us 102 terms. And this is a result of Mathematica. You cannot tell apart the left side from our result. There is slight difference in the error. This is our error, this is Mathematica error. Size is the same. Okay. The point here is not that we have better, smaller number of terms. The point is that we can do it in higher dimensions. Okay. And we did. We have example in 2D. And we were not doing data science. If I were to do it today for data science, I would have an example in, say, 10 dimensions and things like that. For 10 dimensions, you need a lot of points, though. So, and then we did something else, and partitioning of points into groups. And on this topic, I think I have new ideas that probably I'll try to write. And if you know something that I don't know, please tell me, because I know about k-means, I know about some other things, but I don't know practical use of it. And so basically what we did is the following. When you start this reduction algorithm, you need to select the first point. In some sense, it doesn't matter, but in this case, we selected the center of gravity, so to speak, the mean. The result that associated with it, we don't use. And then we run this algorithm, and we stop it after, say, I think 4 terms and 10 terms. We didn't do a very good job with these examples. I can do it much better now. So this is subdivision with 4 terms. And what it finds one of the points. Basically, we find centers of clusters. And the center of clusters is exactly the chosen Gaussian that allows you to represent everybody else. So in this case, you have 4. Here you have 10, the same data. Okay? Now, this approach allows you to find outliers. Now, when we did this, we thought of it as a initial selection of points for Lloyd's algorithm. But now I think it's an independent algorithm. It can be independent. So how do you do this? Well, first of all, you can easily do it multi-resolution. You divide into groups, and you do it again with each group separately. And this is more or less what we did in another paper that I'll mention. And when you suppose you have some points which are far away from the main cluster, it will have to have its own Gaussian. So once you find these groups, you can count number of points in each group. And if you have 10,000 in most of them and 5 in some other group, you know those were outliers. So you can do, oops, yeah. I know about support vector machines which try to find boundaries between groups. But in both cases, you have some optimization. We don't have optimization. I have an algorithm. Now, I'm cheating. There is a little bit of it. Think of the following. Suppose I select very, very flat Gaussians, basically large, 1 over sigma. Sigma is very large. Then this Gram matrix will have rank 1. And then I start moving it slowly, or not so slowly, to make exponent larger, and standard deviation smaller. And at some point, I will see that my algorithm recovers 5 terms, 10 terms, and I can decide on that number and stop. So you can construct these clusters by just running this algorithm. And as long as I'm not trying to do 1,000 clusters at once, it's fast because it's linear in the original number. So you can do multi-resolution clustering, you can find outliers. This needs to be written, I think. But it may have been done, I don't know. So if somebody knows a little bit more about it, please let me know. So this is the paper where we used it for calculations so basically that was 3 dimensions, but we were using Gaussian mixtures. There was no discretization. It's just one algorithm that was run. In quantum chemistry, you can show that integral equations, have convergent iteration. So all we were doing is plug in some initial thing, getting a million Gaussians. We were dividing them into groups, running this algorithm for reduction, putting it back. After 20-some iterations, we had a solution. So basically, this is what I wanted to tell you. Well, that's all.